think in this class we began to talk about atomic size. And as far as atomic size goes, they get the atoms, if you're looking at the periodic table and you go from right to left, they get bigger. And as you go from the top to the bottom, they get even bigger. With fluorine being the smallest and francium being the largest. Now you have the noble gases over here. They're also very small, but technically fluorine is the smallest. And then we have something called ionization energy. And ionization energy is the energy that it takes to remove an electron. So if that's the case, when you think of francium, you've got the nucleus and then a whole bunch of orbitals around it. The orbitals on the very edge are very far from the nucleus. They're relatively easy to pull off. But if you were looking at fluorine is small, so it has a small nucleus, not a small nucleus, it has a nucleus, and then it has maybe a couple of, when I say a couple, I don't just mean two, but it has many fewer orbitals compared to francium. And so the electrons are a lot closer to the nucleus. They're much more difficult to pull off. So ionization energy refers to how much energy does it take to pull off an electron. So in the case of ionization energy, it is easy to pull off the electrons from francium. So as you go up, the ionization energy gets larger. And as you go from the left to the right, the ionization energy gets larger. So you have this inverse relationship here that if you have the atomic size, as the atomic size increases, the ionization energy decreases. You can also kind of think of it as just a way to kind of remember it. Think of a grown-up who's about 50, and that's what we're going to use to represent francium. And then think of fluorine, which is really small, as a 2-year-old. So in this case, the big one has less energy than the small one. And let's see. Do you cover the lowest score from the final? Yes, I do cover the lowest score from the final. 5 points. Yeah, we still have actually 4 more tests in the final. And then you'll turn the picture of your book, of your ACS book, in under assignments, and you'll turn that in on Friday. And yes, I always give bonus points for each test. Okay. All right, so now you kind of got the idea of that. And just to mention electron affinity is the opposite of ionization energy, and it has to do with how much energy does it take to put an electron on, right? No. There's a periodic table that I put on the exam, and you'll see it when you take the exam. It's going to be right at the top of your page. And I made sure that it's clear enough so that when you look at it, you can see the numbers, as opposed to that one time that I put periodic table on there and you couldn't see anything. That was probably not the best. So I made sure by taking a preview of the exam to take a look at it. You might, but you don't have to flip back and forth. You just scroll up to the top of the page. So it's not as bad as it sounds. All right. So let's do an example with an electron configuration. We'll do titanium. And it has 22 electrons. All right. And then we're going to put these in order of, lowest to highest. Now you can either do the Aufbau diagram where you do like 1s, 2s, 3s, then 2p, 3p, and so forth, and then you can draw the little arrows through it and stuff. The other one is to use the periodic table, and when you use the periodic table, you just remember that the period number is the highest n level, and the n level is the energy. So that kind of gives you an idea as you go down the period, what is the highest n level. So if I'm looking at the periodic table, I see that hydrogen and helium are both full. They're in the S block, and they're in period 1. And they're all that's in period 1. So that's 1s2. And then lithium and beryllium are full, so that would be a 2s2. And then boron through neon are full, so that would be 2p6. And then the next is sodium and magnesium, so that's going to be 3s2. And then you've got aluminum all the way through argon, and that is 3p6. And then the next row is potassium and calcium, so that is 4s2. And then we have scandium and titanium, so that's 2 electrons left to go in. And they're going to go into the d orbital because they're in the transition metal, and transition metals are the d block. But notice how it was the 4s because it's in period 4. But with the d's, you always go down 1. So instead of 4, you're going to go 3, and then there are 2 electrons in it. Now, if I'm looking to see how many unpaired electrons I have, in all of these, whatever full subshells I have are not going to have unpaired electrons. For example, a P, if it has all 6, is going to look like this. Those are all paired. So I know that these S's are full, the P is full, the S here, this P is full, and even this S is full. So all I have to do in this case is draw this out. All right. So I know that I have D2. And according to Hund's rule, I have to put 1 in each before I start doubling up. So they're going to get their own orbital. Getting their own orbital, that allows me to see how many are unpaired. And in this case, this one is unpaired, and this one is unpaired. So it has 2 unpaired electrons. And that's how you can count how many unpaired electrons there are. Let's see. That's a good question. The reason is because when you have this, you have a D2. It's very far from being half full, and it's very far from being completely full. So it's just not more stable to put an electron in the D there. The exceptions you kind of have to memorize. It's good to kind of get the trend, and if you have time, then memorize them. Because there are a couple of weird ones in there. But I think you'll be okay as long as that you know that if you would have expected a D4, so you had some S2 and then a D4, that 4 is going to become a 5 and the 2 is going to become a 1. And then if you had a D9 and an S2, you're going to get that. In a lot of cases, the 8s will also go up to 10s. There are some weird situations like cobalt is pretty normal. Say ruthenium's kind of weird. You just kind of have to look at the periodic table and kind of go over it and practice it a few times, but you'll see there. All right. Actually, to find the core electrons in this situation, the core electrons are going to be the ones that aren't valence. To find the valence electrons, it's kind of strange because you would think that the D would be involved in valence, but it's not. only the highest N level is valence. Sure. Yep, we can do that. Yep, that is true. Well, let's see. Calcium would be 1, 2, 3, 4s2. And then in this case, calcium doesn't have any D's at all because it ends in column 2. And so it being in column 2, the highest N level that you're going to see is the 4. And so that's going to be your valence electrons. You can also go by the fact that it's in column 2 because remember, the number of valence electrons is exactly the same as the column number when you use the AB numbering system. So what I'm talking about there is you have your periodic table. Then you have column 1, column 2, 3, 4, 5, 6, 7, and 8. So to find the valence electrons here, this column has 1, this was 2, 3, 4, 5, 6, 7, and 8. So those you can go by the column number or the group number they're in. Right in here, this is where you have to do, like in all of this area here, that's where you have to do the electron. All right. And let's see, I thought you could not do brackets unless, yeah, actually that is, oh, okay, I see what you're saying. You don't mean the same with calcium, you mean titanium. Okay. So for titanium, if you were going to do the condensed version of that, you have to use noble gas. The noble gas closest is argon, that is closest without going over. And then it would be 4s2, 3d2. But you wouldn't be able to use calcium because it's not a noble gas. On the periodic table, I don't remember if the period numbers are on there, but the periods literally, you can just count them 1, 2, 3, 4, 5, like that. They just go in that order. And with the AB numbering system, these are all A's and these are B's. And I'm not going to ask you about how to number the B's. The other system is the 1 through 18, and you literally just count 1, 2, 3, 4, 5, all the way until you get to 18 over here. So let's do an example of the Rydberg equation. My favorite version of that is the one where it's delta E equals negative 2.178 times 10 to the negative 18, 1 over n final squared minus 1 over n initial squared. Okay, and this gives you the energy of the change in energy, which is the energy of a photon. So let's say we were going from n equals 2 to n equals 3. If that's the case, then I would do it like this. Delta E equals negative 2 point, and if you round this to 2.18, which a lot of places you'll see that, the number becomes easier to memorize because it's negative 2.18 times 10 to the negative 18. So you get the 18 and 18 there. It becomes 1 over, the n final is 3, minus 1 over n initial, which I don't know why I'm writing that. N initial is 2, so that's 2 squared. And then it would just be a matter of putting this in the calculator. So negative 2.18 times 10 to the negative 18, 1 over 9 minus 1 over 4, and then basically just solve the rest there. Sure. Yep. Okay. So let's do another one. Instead of putting this in the calculator, because that would take extra time, I'm going to move on to the next one, and we're going to do one where the electron is what's called ionized. So with ionization energy, that means you're pulling off an electron. The electron's no longer associated with the atom. So if they say that you have an electron, it goes from n equals 2, and then it's ionized, that means n initial is 2 and n final is infinity. If that was the case, you'd have this 1 over n final, which is infinity squared, minus 1 over n initial. N initial is 2, so 2 squared is 4. Now, what you have to remember, if you do a limit on this, the limit as it approaches infinity is 0. So this whole thing goes to 0. So then you just have negative 2.18 times 10 to the negative 18 times 0 minus 1 over 4. So then basically you just have this times negative 1/4. And then, let's see. Actually, it doesn't matter which version of the Rydberg equation that you use. Let me show you why. One of them is 1 over lambda equals r times 1 over n1 minus 1 over n2, and those are both squared. In this case, n1 is just going to be the lower number, and then, or the lower energy level, which is always the lower number. And then n2 is going to be the larger number, or the higher. So if we were going from 2 to 3, 3 goes here, and 2 goes here, just because it's the higher and the large, and the smaller and the bigger. It's different with the other Rydberg equation. But this Rydberg equation, what you can solve for is lambda. Let's say you had to solve and find the energy level, and you used this equation. You haven't done anything wrong because you still have this equation. And so you plug this wavelength into this, and then put in your constants, and then solve for the energy level. The other one is delta E equals negative 2.18 times 10 to the negative 18, 1 over n final squared minus 1 over n initial squared. And in that case, if I was to solve for energy, I'd get it directly from here. The other thing is, if I was asked to solve for wavelength, I could still use this equation because I would have E equals hc over lambda. I would plug in my energy here. These two are constants, and I would just solve for the wavelength. All right. Example where we'd have to solve, yeah, I can do that too. All right. Oh, Chad, you have a question.
Yep, so when you're trying to solve for wavelength after you got the energy, will you rearrange the equation like wavelength equals hc divided by E?
Yeah, you could definitely do that. So what that would look like is you have E equals hc over lambda, and then you multiply both sides by the wavelength, so that cancels on this side. Then you have lambda E equals hc. Then you just divide by E. That cancels. And then in the end, you end up with lambda equals hc over E. So you can rearrange the equation first, or you can plug it in and just solve for it. Either way works. And then 1 over wavelength is actually called the wave number, which is a bizarre thing to call it. It's just the inverse of the wavelength. The frequency is c over lambda. Yes. Depending on which one of the Rydberg equations you're using. You could get wavelength first, or you could get energy first. It depends on which one of the equations you choose to use, and it doesn't matter which one, just which one you like better. Because the energy is related to the wavelength. So if you solve for energy, you can still get to wavelength. Oh, hang on, guys. Oh, for crying out loud. Okay, sorry, my computer went on fritz there for a second. All right, so let's do one where we're looking for n initial. That's a pretty common one. It's got delta E equals negative 2.18 times 10 to the negative 18, 1 over n final squared minus 1 over n initial squared. So let's just, I think the easiest way to do this. All right, so let's say our energy was 2.3 times 10 to the negative 19 joules. And n final was 3. And we're looking to see what n initial is. Yes, I did send out an email with all the topics that are going to be covered on the exam. All right, so if you check your email, you'll find it in there. All right, so this becomes 2.3 times 10 to the negative 19 joules equals negative 2.18 times 10 to the negative 18 times 1 over 9 minus 1 over n initial squared. So in this case, I would divide both sides by this. All right, and that would be negative 2.18 times 10 to the negative 19. And then that's going to give you a negative number. I'm just going to call this negative number to save time and not put it in the calculator. That cancels. And then it becomes 1 over 9 minus 1 over n initial. So I'm going to subtract this from both sides. So my negative number minus 1/9 equals 1 over n initial squared. So if I multiply both sides by n initial squared, then I get n initial squared times my number minus 1 over 9. And then I'm just going to divide by this right here. And then I'm going to move this up to the top of the page. Then I get n initial squared equals 1 over negative number minus 1 over 9. And then I'll take the square root of both sides and get the answer. So I'm assuming I made up this number here. I have no idea if that would even make sense. But in this case, you should get a positive number here. You wouldn't actually end up with a negative number, because then that would give you an imaginary number in the thing there. What did I divide by? You mean here? Okay. What I divided by was, I just had, if you look here, that's just the original equation. So what I divided by on both sides was this constant. So the constant goes away on this side and it shows back up over here. Function problem, so we'll do one of those. Patrick, you have a question.
Okay, so I know on one of the questions for the homework, it